know completely how to find an antiderivative of rational fraction. So this is what we will learn today. Okay, so integration of rational fraction. But to do that, we will need the following theorem. So the first, yes, here is the theorem. We will write it here and see what we can learn from it. So we have two polynomials. We have to form a fraction. Okay, let's say the denominator is the polynomial q of x. Okay, so q of x, we can any polynomial, we show that any polynomial with real coefficients can be factored. Factored how? There will be a constant, then terms with degree 1, with linear terms like that, with root r, with a power, some power m. Then let's say we have several roots. Okay, so product, continue, and the last root, simple root like that. We call them simple root or multiple root. Okay, s n. Okay, and then there will be terms with second degree that doesn't have a root, so we can write them in this form: x2 plus alpha x plus beta to power p, then continue other factors and similar factors, x2 plus gamma x plus delta power q. So we have to specify that they don't have root, so it's enough to say that the delta, that is alpha square minus 4 beta, is negative, and gamma square, etc. the others also, gamma square minus 4 delta is negative. Okay, so then we have to write, so this is well known in algebra, and now any fraction in the form px over q of x, so you have polynomial over polynomial. So when you write, we can write it as follow. We can have, we make a division, Euclidean division, to get a polynomial. So this part is obtained by Euclidean division. So let's write here, obtained by Euclidean division. We will see an example later. Okay, then the other terms, the following terms, for the terms that are related to this factor in the denominator, q of x. Okay, the term related to this factor that appears in the denominator will be in the following shape. So there will be a constant em over x minus r power m. There will be then another constant minus, let's say a minus m x. We decrease by 1 degree the degree here. Okay, and let's continue up to, okay, e1 over, so x minus r degree 1. Okay, and we do the same thing for all terms similar to this one. So the last one, for example, we will have something like let's call it bn over x minus s power n plus bn minus 1 over x minus s power n minus 1, etc. We decrease by 1 degree the power until the last term b1 x minus s degree 1 here. The polynomial is degree 1. Okay, now what about the terms with second degree polynomials here? So there will be decomposition in terms in this shape. So a linear term, so linear degree 1, let's call it dp over the x2 plus alpha x plus beta power p. Then we decrease again by degree 1 the denominator. So we will have something cp minus 1x plus dp minus 1 over, okay, over x2 plus alpha x plus beta power p minus 1. We decrease until we reach degree 1. So c1x plus d1 over x2 plus alpha x plus beta. We stop and we continue with like that with all similar terms until the last one. So we will get again, we will have eq x plus dq over x2 plus gamma x plus delta power q. Okay, and we decrease then linear term over something degree less by 1 unit. So eq minus 1 x plus dq minus 1 over, okay, over x2 plus gamma x plus delta power q minus 1 plus then so e1 x plus d1 f instead d, sorry, here f is not necessarily the same, but there is a symbol f, yes, q, which is, yes, which is different. So f q minus 1 f1 over x2 plus gamma x plus delta. Okay, so this is what the theorem says, and it is the key for us to find antiderivatives. So this is the key. Because we have the following decomposition possible, then the calculation of integrals is made easier. So here it is. So let's, oh, it's not a good one. Okay. So term, so I want to write here by this side, so maybe I use the color black color better. Okay, so for a term like this one, for example, so 1 over x minus r. Now if I want to integrate, find an antiderivative of the fraction, then it will be the sum of antiderivative of each term. So the simplest one, of course, is for a. That's one. A of x, let's say dx, it's something polynomial. Let's say, how we call the coefficients, we call them c1 alpha, or not beta, t1. So it's polynomial. Let's yes, it's a sum of tk xk. Okay, k from 1 to, we don't know, a degree. Let's call it m, n now, capital N. So it will be something like that. So it will be tk, okay, xk plus 1 over capital K plus 1. Okay, so this is polynomial. You know how to do it. Plus a constant c1. For terms like this one, we know it's ln absolute value x minus r plus a constant. Terms with one like that, x minus r power m dx, but with m greater than 1. Here m is equal 1, we have ln. Here then it's polynomial x minus, we can write it, remember, we can always write something like that, minus m dx, and get then an antiderivative, which will be in the form x minus r minus m plus 1 over minus m plus 1 plus a constant. Okay, So finally, you see the two rows already. For the first three rows, we know completely how to compute, find an antiderivative. Let's now explore what is happening for terms like this one, the simplest one, then see what we can do for with highest degree p. Okay, so let's do that. So let's give the idea how it works. So if I have, then now let's concentrate C1, something like Cx plus D over x2 plus alpha x plus beta. Okay, so degree 1. Okay, so I need to work on this term. I see that the derivative of denominator is 2x plus alpha. So if I make up here a term like that here, so I can use substitution and get an ln. Okay, so let's make it appear. So C, I want 2x plus alpha. Okay, over, so I have my term beta. But I don't have, if I develop, I have 2cx. I have only cx, so I need to divide by 2. So that when I divide and substitute, when I distribute, I will get cx, yes. Then another term, c2 times alpha, which is not here. So I will subtract it, d minus c over 2 alpha. Now I will separate my integral. Okay, I will have to this first integral, which I know. I did everything so that it works for me. Okay, then this factor, this is a constant, I put it outside, and 1 over x2 plus alpha x plus beta dx. You see, so for this one I know that I will get, so let's do it here. So let's write it here. For 2x plus alpha over, well, let's use another color. Okay, so for 2x plus alpha over x2 plus alpha x plus beta, so you remember, you know how to do it. So we can use just u as the denominator. So it will be ln. Okay, it's like du 1 over u. Okay, this is my u. Okay, so I will get ln absolute value of u plus a constant, which is ln absolute value of x2 plus alpha x plus beta plus a constant. Now the remaining term is this one. We need to work on this one. This one needs more work. So look at this, the idea how it will be solved. So here it is. So let's focus on this one now. We have this time something 1 over x2 plus alpha x plus beta. So just 1. Okay, so the idea is to work on to complete the square of the denominator. If I complete, I will get alpha over 2 square plus beta minus alpha 2 over 4 dx. Okay, now let's call this constant a square. Okay, so let's call this quantity a square. A square is beta minus alpha 2 over 4. Remember, it's for beta minus alpha 2 over 4, so it is positive by the assumption we did previously at the beginning. Okay, so this term, and set the substitution u equal x plus alpha over 2, so du will be dx. So I will have then 1 over u2 plus e2 du. Okay, and now I see that I am close. It looks like that I have a tangent, like an arctangent. So I need just to do some work here. It's 1 over u over a square factor. Okay, and we have then 1 over e2 and the du. If you use another substitution, u over a, d capital U is 1 over a du. Okay, then so it is reduced to du over du integral 1 over a du 1 over u square plus 1, and this is exactly 1 over a arctangent of u plus a constant, which is 1 over a arctangent, okay, of u over small a plus a constant, then come back to the original variable. Okay, so it will be in the form arctangent of x plus alpha over 2 plus a constant. So you see, this is the hardest part of to find an antiderivative. Now the last one that we need to find is when we have higher degree here. When you have a denominator with a second degree, okay, when you have here a higher degree, so how you will do it? So usually, so we bring ourselves, so we do the following transformation. We bring ourselves to something, a constant, over x2 plus alpha x plus beta power p, okay? So, and thus we transform them in the form du something, okay? u2 plus e2, okay, p, and we use integration by parts, okay, and use integration by parts. Sorry. Use integration by parts. So this is the main idea, the main steps to follow in order to find an antiderivative of a fraction. So you need to decompose first, to write your fraction in simple elements following the theorem, okay, then integrate term by term, and you can also with terms simple like that, or with degree, second degree, and each of them you know exactly the pattern to follow, the method to follow, and it works always. Okay.